All right, thank you all for sticking through to the break. So today I'm going to be talking about a lot of the development that we've been doing over at the U of A and some recent opportunities that just came up. There we go. So for those that don't know, seismometers have been part of lunar exploration since we started landing people on the moon. So for every landed mission, so Apollo 11 through 17, obviously not 13. If you don't know why, watch the Tom Hanks movie. Um, and from 12 on, they were able to start building up a seismic network on the moon. So this is really the only seismic network that we had beyond Earth. And they were able to find a lot of key scientific findings through the use of seismometers. Notably, they were able to confirm the Earth is differentiated. So it has a crust, mantle, and core. Notably, that is still up for debate whether or not you have a liquid outer core or partial melt layer. We noted that one of the most common types of events are deep moonquakes. So these are events that are caused by tidal interactions between the Earth and the moon. So as the moon is essentially creating tides on Earth, we are creating moonquakes on the moon. Notably, might be a little hard to see here. So all these deep moonquakes are essentially on the near side and not so much during the equatorial, or excuse me, the polar regions. So that's probably due to one of the limitations of the Apollo seismic network. And that's the fact that all of the stations, mostly due to just ease of engineering, were all located within 30 degrees of the equator and all on the near side. Which basically means that we have this bias where we see a lot of stuff going on the near side of the moon, but we really have no idea what's going on the far side of the moon, beyond what we've seen from other spacecraft since then. So the deep interior is still a huge question mark, especially seismically. Addition to some of the deep moonquakes, we were also able to see impacts. So this was actually really important because we were able to use radioisotope dating to figure out the ages of different cratered regions, and we know the current impact rate and how many craters we currently see on the moon. We're able to take that sort of crater counting approach and apply it elsewhere in the solar system, which is how we know like rough ages of different bodies or different surfaces in the solar system. Also notably, and I get this question all the time, there are no plate tectonics on the moon. The Earth is the only confirmed body with plate tectonics. However, the moon is essentially shrinking as it cools down. So if you kind of picture like a fruit that gets overripe and gets like wrinkles on it, the formation of those wrinkles ends up creating seismic events. So we're able to measure those. They can actually be quite significant in size in terms of like seismic magnitude, and they could potentially pose a risk for astronauts or for any more permanent type structures we want to build. So for those reasons, it's really important that we head back to the moon and we collect more data so we can better assess things like seismic risk and start to answer questions about the parts of the moon that weren't explored. Also of note, at the time, the seismometers were really great technology, but it has been 50 years and seismometers have come a really long way. One of the biggest things is the fact that we're digital now. So if you look at the seismograms in this figure here, if you're not a seismologist and they just look like squiggles to you, I totally get that. But they're really kind of crap quality. You have to like stack them and do tons of filtering and special signal processing in order to be able to even start to identify seismic waves that are useful for looking at the interior. Our new seismometers don't have that issue. So there's been a couple of opportunities, and I've highlighted the ones in yellow that we've actually been funded to do. So there's the Dolly Matisse program through ROSES. That's instrument development. Dolly is essentially Matisse, but focused on the moon, for those that aren't aware. And what they essentially do is they take a instrument from TRL-4 up to TRL-6 with the idea that by the end of this project, you should be flight ready. So you could go ahead and propose to a flight opportunity. We've also applied for CLIPS prisms. So this is the commercial lunar payload services, and then instruments that would go on those commercial payloads. So one seismometer was selected out of JPL. So I think it's due now to launch and land in 2025. We'll see if that gets pushed back again. Notably, that is going to be attached to a lander and not actually touch the lunar surface, which is an important caveat I'm going to bring up in the next couple of slides. But really exciting, and we only found out about this like a month ago, is we were selected to send seismometers as part of the Artemis program. So as many of you probably know, Artemis is going to be the follow-on to Apollo, and it's going to be an incredibly rare opportunity in planetary sciences to have humans deploy your instruments, which for a seismometer is kind of huge. So Artemis should be launching in September 2026. It's kind of akin to Apollo 11 in the sense that it's going to be the first of many, hopefully, that will actually land on the moon and have astronauts walk around. So LEMS is one of 3 instrument payloads that the astronauts will be bringing with them. There are numerous science goals that Artemis wants to address, and I've highlighted the ones in yellow that the seismometer alone could address. So things like planetary processes. So how often are those wrinkle ridges going on? What is sort of the tectonic state if it's not plate tectonics? We can look at the history of volcanism by identifying volcanic terrains and seeing like how thick different deposits are. We can also look at impacts, the current rate. What does an impact crater look like on the moon? Especially the South Pole Atkin Basin is believed to be a really large impact crater. So we can actually image and see what might be left of it beneath the surface. And of course, we can also look at, since we're heading to the South Pole, we can actually really answer, is the outer core liquid? Is it partial melt? How big is the core? And is the far side and the near side actually kind of similar, or is that dichotomy that you see at the surface extending all the way down to the core mantle boundary? So we can further address the impact history of the moon by looking at the current impact rate and sort of, what does the South Pole basin look like as an impact area? And then lastly, we can start to really address the risks associated with seismic hazards. So are you going to have a scenario where you could potentially have a magnitude 4.8, 5 that could be damaging if you're nearby? Or is this something where they are going to occur so rarely? It's kind of like that earthquake in New Jersey. It makes big news because it doesn't happen that often, but the damage was incredibly minimal. So just to kind of show how we fit in at LPL, we've been developing seismometers for essentially a decade now, and we've been working with a company called Silicon Audio. And through a partnership with them, we've already brought in, not including LEMS, $12 million into the university through various programs. That includes things like P-STAR, which is where those 2 photos come from. They allowed us to test our instrument out in the field. Those experiments were more geared toward icy moons, which is why we're in Alaska and Greenland with ice. But we also did IC2, which is an instrument development program for icy ocean worlds, Dolly and Matisse as well. The current Matisse that we're funded on is for binary asteroids. So we're looking at how seismometers can help look at asteroid interiors and potentially identify their structures. But yeah, most excitingly was LEMS was selected for the Artemis Deployed Instruments call. So that's going to be our focus for the next 2 years, essentially. And we are going to be supplying the seismometers for that. So to give you an idea of how good these sensors are, our SP is roughly the size of essentially a soda can coffee cup. Our VBB is a little bit bigger than that, but they're still quite small and compact, and they're really sensitive. Our short period is roughly the same sensitivity as the InSight short period seismometer. Our VBB, in theory, can get down to the InSight VBB seismometer. We're still working out a few kinks there, so we're not quite there. But we're quiet enough that we should be able to detect like asteroid seismicity just from the tidal interactions between the binary system. And when we head to the moon, we should be able to detect thousands of events over our initial 3-month up to 2-year lifetime. One of the other great things about our instruments is we're tilt tolerant. So we can be tilted up to 30 degrees and still work, which when you think about an astronaut deploying something, like you almost have to try to get it at a 30-degree angle. Like that's pretty steep. To put that into context, the InSight seismometers had to be within half a degree. So they had to bring like leveling mechanisms with them. So we definitely have an advantage over that. We also don't have to be in a vacuum. It helps, it makes us better, but it's not a requirement, which will help if we do eventually head back to Mars or something like Titan, which has an atmosphere. But as you can see here from the curves, if you fall above the blue and red line here, it basically means you can detect it. So there's essentially almost every type of event you would want to detect. We should be able to do it through a combination of our short period and broadband instrument. So deep moonquakes, shallow moonquakes, impacts, thermal moonquakes, which are essentially these little smaller events that are very common and basically happen because the moon is heating up and cooling down very rapidly. So all of those we should be able to detect and build up a really nice catalog. And once we have those higher quality events, we can use those to look at interior surface or interior structures. One of the really great things about seismometers is that we can do science from the surface all the way down to the inner core, which is not something a lot of other methods can do. They're typically limited in their range. So for future plans, we'll be working on LEMS for the next 2 years, which is really exciting. We're going to continue to develop our seismometers. We're looking at potentially making them less power intensive, and also where they could potentially be deployed by something like a drone. So for something like on Mars, we could build up a network that way. And then we're also looking forward to additional PRISM, SALSA calls, and there's no reason we can't keep submitting to Artemis and build up a network like we did for Apollo. So with that, I'll take any questions.
Thanks, Angela. Do we have a question? Oh, I see.
Very nice talk. I had a question about what coverage is needed with the seismometers on the moon to actually reconstruct the core, and what level of, like, I don't know, how precise are you trying to be with where the inner core is, core mantle boundary and all that stuff?
Yeah, it's a really great question. So before 2016, a lot of people would have said you need a network of seismometers because that's how we've done it on Earth and the moon. But InSight on Mars showed that you can actually recover the core with very few events. On the science side, that's actually what I do when I'm not developing instruments. So we can get, the size of the core with very few events. So within 3 months, we'll have enough data to be able to do that. In terms of the uncertainty, it kind of will depend a little bit on where we see the events coming from and how many of them are. Again, to give you an idea, with InSight on Mars, they were able to get the core within plus or minus 30 kilometers. On Earth, we know it to like 1 kilometer, but that's also because we have thousands of events and thousands of seismometers. So we're looking at, I would say, on the order of, tens of kilometers uncertainty for the moon.
Nice talk. Can you comment on the swap of your instrument?
The what of my
The
instrument?
swap, the size, weight, and power.
Oh,
consumption.
okay, yeah. So size of the actual sensors, the SP is, yeah, like I said, roughly the size of like a soda can. Walt actually had the VBB up in his initial talk. That's a wee bit bigger. I forget the actual dimensions once it's in the housing. For power, the sensors operate at about 120 milliwatts total for the 3 axes. So double that for the SP and VBB. Weight, the SP is, I want to say 2 kilograms once it's in the housing. The VBB's a little bit heavier, but I want to say it's on the order of like 10 kilograms. So still pretty light. Am I forgetting one? Or what's the A in swap? And, oh,
Hey, and
okay,
yeah.
never mind, then I'm good. Okay, sorry.
And so you showed the measured noise floors of your instrument, but of course there's also, when you test them here on ground, the microseism and basically the background noise of Earth. How are you actually measuring the noise floor of the instrument?
Yeah, so that I put up is we can essentially remove Earth's noise floor. So we can estimate what it would be once we get on the moon.
Okay, so it's basically a model.
Yeah, I mean, it's a really good model, but yeah, it's a model.
Understood.
Yeah.
Thanks.
Appreciate it. Uwe Hilgert, Bio5 Institute. The reason I'm saying that to make clear that I really have no clue. Here's my question. Does your instrument also lend itself to composition analysis, to prospection kind of investigations?
Yes and no. So again, just doing a callback to Insight, they were able to get like very broad composition in like the way of we know the inner core or the core on Mars is relatively heavy in terms of light elements. So like that sort of broad composition we can do. We can also look for things like icy deposits on the moon to say like if we think there's a certain ice content. But it's not going to be quite the same as if you bring a core back and you say like it's this much plagioclase or anorthosite or its ice content is down to this weight percentage. We can just sort of ballpark it through the seismic velocities that we recover and say they mostly align with this sort of mineralogy.